Welcome back to Biomechanics Lab. This is going to be our lecture over Chapter 2 in your textbook, and it concerns biomechanics of skeletal muscles. Alright, so I've got these two pictures right here. This is the anterior side of a person in anatomical position, and this is the posterior side. And these figures just show the major muscles, and we're not going to spend time going through all of these, but I will preface this chapter by saying this. We're going to spend many weeks after this, and we're going to be looking at specific joints. So for example, one week we would be looking, say, at the shoulder joint. Another week we'd be looking at the hip joint, another the knee joint, etc. And we'll get familiar with all of the major muscle groups of that particular area. Okay? So for example, if we were looking at the arm, we'll definitely look at the bicep brachii, we'll look at the tricep, which is going to be on the back side. We'll also look at, say, the brachioradialis, and we'll look at the, if we're talking about the shoulder, we'll look at the deltoid. Okay? So we'll get probably most of these, and we'll learn about those as we go throughout the weeks. One thing I do want to mention is that we've got two more directional terms, and that's superficial and deep. And one of the, what those mean is superficial means towards the surface, whereas deep means more towards the interior of the body. So if you think about it, just something pretty easy to rationalize, the skin, your skin would be superficial to, say, your heart, which is deep. Okay, deep just means more on the inside, superficial means more on the outside. Well, sometimes we can have major muscle groups that are either superficial or deep. So one thing I'll mention is we've got this muscle right here called the transverse abdominis, and then we also have a muscle called the rectus abdominis. And the rectus abdominis, that's kind of like what you typically see, the six-pack. Those are the ab muscles that you could potentially see, but the transverse abdominis is another abdominal muscle group that's deep to the rectus abdominis. So we can have some that are superficial and some that are deep. All right, let's talk briefly about muscle shape and fiber arrangement. All right, so we're going to have two kinds of shapes of muscle fibers. We're either going to have parallel muscle fibers or pinnate muscle fibers. Now, obviously with parallel muscle fibers, their name basically just means that the muscle fibers themselves run parallel to each other, roughly. Okay? And parallel muscle fibers generally do not provide as much force. They usually provide a greater range of motion. Okay? Now, if we talk about the pinnate muscle fibers, what you'll see is this white thing right here in each of these. These are tendons, okay? In pinnate muscle fibers, the muscle fibers do not just run parallel to each other. Rather, they radiate away from that tendon, okay? Now, what that causes is pinnate fibers tend to have a lower range of motion, but they can generate more power. Okay, so these tend to be stronger muscles. And I'll just mention this. Unipinnate means that from this tendon we only have fibers radiating in one direction. Bipinnate means we have a tendon kind of in the middle, and we have the muscle fibers radiating from both sides. Then multipinnate, we have several tendons, and we have the muscle fibers running away from each of those tendons, okay, each part of it. So this one, that one, and that one. Therefore, it's multi-pinning. Okay? Okay, now let's get into some muscle contraction. Okay, so let's look at first these pictures right here on the left side. Okay, so in this situation, this is kind of like if you're just doing a typical barbell curl. So you got either a dumbbell in your hand, got a barbell curl, you're doing flexion of the arm, okay? This has to do with, is the force that your muscles are providing greater or less than the force of what you're trying to lift? Okay, so in case A, if your muscles in your arm are providing more force than the weight of this object, then you'll be lifting the object up. In fact, if you can imagine this, you'll be, as long as the elbow stays in the same position, you'll be decreasing the angle of the joint. Okay? As we'll talk about in a minute, that's called a concentric contraction. Okay? And seeing as I'm moving this weight up by decreasing the angle of the joint, that means my bicep brachii is in a concentric contraction because it's shortening. Now, if the force provided by my arm is exactly equal and opposite to the force or the weight of that object, then nothing happens. It doesn't move. Okay, so that's sort of like if you did an isometric contraction. That's if you just had the barbell in your hand or dumbbell and you're just holding it static. Okay, that's called an isometric contraction. And because the force provided by the arm is equal to the force of the weight of the object, there's no change in the length of the muscle, and that's what isometric means. Okay, no change in the length of the bicep. Now, if the bicep provides less force than the weight of this object, then the bicep is actually going to be in the eccentric phase. It's going to be doing an eccentric contraction because it's lengthening while lifting the load. And that's going to cause the angle of this elbow joint to increase, and the arm extends and lowers the weight down. All right? Now, these were all for the bicep. Now, if I change the situation where rather than directly lifting the object up, if I now have to pull a string down to lift the object up because I'm dealing with a pulley system, now the muscle that's contracting is the triceps. Very similarly to the bicep example, if the tricep shortens, then the tricep is going to be doing a concentric contraction. Okay? And that's going to cause this string to move down, which forces this object up. And that's under the situation where the tricep is providing more force than the weight of this object. Now again, if the tricep provides a force exactly equal and opposite to the weight of this object, the object doesn't move. The string doesn't move, the object doesn't move because the forces are equal. And again, that's an isometric contraction. Now, if the triceps provide a force less than the weight of this object, then this string is actually going to move up and the triceps will be lengthening and they'll be in the eccentric phase of contraction. And that will cause this object to then move downwards. Okay? So now we've got this nice table that summarizes isometric, concentric, and eccentric contractions. Okay, the agonist, this is a term that means the muscle that's causing the movement. So for example, in these left pictures, the bicep was the agonist. In these right hand pictures, the tricep was the agonist. Turns out for isometric contractions, again, no change in length of the agonist. When it's a concentric contraction, the agonist shortens, and when it's an eccentric contraction, the agonist lengthens. All right. Now, one other thing that's also important is if we're talking about how does the muscle force compare to the resistance. This is actually a misprint. For isometric contractions, the force is equal to the resistance. That's what we said for these middle ones. The force provided by the muscle is exactly equal and opposite to the weight of the object, or the resistance. In concentric contractions, the force that the muscles provide is greater than the resistance, whereas for eccentric contractions, the force is less than the resistance of the object. Okay? One other thing that's also probably important is if we're talking about acceleration versus deceleration, isometric contractions, obviously there's no acceleration of the object because there's no change in length of the muscle. It doesn't move. But for concentric contractions, these are usually for accelerating something, and they tend to cause motion. Okay? Eccentric contractions are usually used for decelerating, and they tend to control motion. Okay, you might have heard whenever you're doing the eccentric contraction of various weightlifting techniques. So for example, when you're doing bicep curls, the eccentric contraction is when you move the barbell down. They often say, make sure to do it slowly because that's the point. You're controlling the barbell down. Okay? All right. This is where we're going to get into something that's really important for the lab purposes, particularly for your project. All right. We know that muscles don't just contract. If you've taken anatomy and physiology, which hopefully you have, and maybe exercise physiology, you know that a muscle, in order to contract, it has to be stimulated by a motor neuron. Okay? Now, neurons that go toward and away from the spinal cord, they tend to be arranged in a network called a plexus, and there's various plexuses that we have. For example, this is the cervical plexus, which contains spinal nerves C1 through C4. Another example, the brachial plexus originates from spinal nerve C5 to thoracic 1 or T1. And one other thing that's important to know is if we've got a neuron that's going toward the spinal cord, that's a sensory neuron because it's providing information back to the brain. whereas a motor neuron would go from the spinal cord to an effector organ such as a muscle. Okay, all right. This figure is kind of showing which regions control what. Now, it makes a little bit of sense because at the top you would expect that to control head movement, and as you go further down, they control different things. Okay, a better way to look at this is we have these tables right here, and by no means do you have to memorize all of these. I'm not even going to ask anything about this on the quizzes, but you notice that C1, it tells you what it controls. If we're talking about the sensory system, it's involved in touch at the vertex of the skull. Whereas the motor parts, the C1, the motor neurons originating from C1, control upper neck muscles. Okay, just take another example, T1. The sensory component neurons of T1, those control or sense touch of the medial arm and forearm to wrist. Whereas the motor neurons that come from T1 are going to control the intrinsic muscles of the hand except for opponens pollicis and abductor pollicis brevis. Okay, so this table just kind of gives you a little bit of an understanding that each spinal nerve, or the nerve root, and remember we have sensory neurons that go toward the nerve root, and then we have motor neurons that go from that towards the muscle to control it, but each one is going to control a different part of the body. And here's some more that goes down to the coccyx nerve. Okay. Now, as we've mentioned, in order to contract a muscle, I don't care what the muscle is, it has to be innervated and stimulated by a motor neuron. Okay? So one thing that is very, very important is that you understand what a motor unit is. All right? So a motor unit is a motor neuron plus all of the muscle fibers that motor neuron innervates. Or we could just simply say a motor neuron and all of the muscle fibers it innervates. Okay? So for example, here we've got one motor unit. All right? Here's the motor neuron, and you can see it's innervating all of these muscle fibers. Okay? Now, depending on what kind of contraction we're doing. So for example, if we're doing something that doesn't require a lot of force, such as writing on a piece of paper with your pencil, okay? That's not going to require a lot of force. Also, blinking your eyes doesn't require a lot of force. Those activities that don't require a lot of force have a tendency to have few motor units activated. If we've got an activity that requires more force, such as running, and especially things like weightlifting, we're going to need much more motor units activated. And so we have this relationship that says the more force that a muscle needs to provide, the more motor units that will be activated in that muscle. So for example, if we did bicep curls, and we did 10 pounds, 20 pounds, 30 pounds, 40 pounds, and 50 pounds, what we would see going from 10 to 50 pounds is that each one of those situations you would detect more motor units activated. And we're actually going to look at electromyography to determine that, and we're going to measure the electrical activity of the muscle, and that's representative of the motor units that are activated. We're not going to do that this week, but we'll be doing that in the future, and you may be doing your project over that. Okay? So this is a little table that describes if I've got some electrical stimulus, okay, increasing stimulus strengths, then I get more tension provided by the muscle. Okay? Tension is just the force. So here I have a subthreshold stimulus. If it's subthreshold, it didn't meet threshold, so there's no contraction, no tension observed. Now if I've got a threshold stimulus, something that actually reached threshold, I got a little tension, all right? And if I have more and more stimulus, I'm going to have more and more force produced, okay? Now if I get a maximal stimulus, I can't really get any more force than that, okay, generally. So even if I provide a supramaximal stimulus, or in other words, greater than a maximal electrical stimulus, you can only lift so much. You can only provide so much force by the muscles. Okay? This is true to an extent, but there's some phenomenon that we're going to look at in just a minute. Okay? One thing I want to show here is that there's actually a delay period once you have the electrical stimulus. It's called the latent period. Then you get the contraction, and what's very important to what we're about to talk about is you have a relaxation phase. Okay? So a little latent period where there's a delay, a contraction phase, and a relaxation phase. Okay. This is something that's showing something called wave summation or just summation and tetanus. So here's what happens. Let's say I have just simple electrical stimuli, all right? Just these two right here. Okay, I'm going to get some force, okay, then I relax. Then I get another electrical stimulus force and relax. Now over here, what if I do something where rather than let the muscle completely relax, I apply another electrical stimulus before it's finished relaxing? Well, if you do that, it turns out that the electrical stimuli are going to summate or add together, and as long as you don't let the muscle relax, you can actually increase the force just by applying electrical stimuli before the muscle can relax, and you actually end up being able to generate more force. Now, these little lines right here represent the frequency of the electrical stimulus. So here it's not very frequent. As you go to the right, they're really frequent. Well, if you get really, really frequent electrical stimuli, you can get something where the electrical signal kind of looks like just a line, not like this up and down. This is called tetanus or fused tetanus, okay, where you don't actually see the contraction and relaxation, any of it. It just looks like just a line, okay? So the point is you can actually end up generating more force. We've got another similar phenomenon called TREP, which is a little bit different. In all of these, you're actually going to you're going to apply an electrical stimulus, but you're going to let the muscle relax before you apply the next stimulus. You'll notice that these stimuli are all constant strength, but it turns out that if you let the muscle relax, and then you do another contraction, and then you let it relax, another contraction, etc., it turns out that over time, even when the stimulus is constant strength, the amount of tension produced by the muscle can actually increase over time, and it will sort of level off. And as long as you're letting it relax before you apply the next electrical stimulus, that's referred to as TREP. Okay? Another biomechanical phenomenon is that you actually don't get the maximum tension in the muscle at 100% of its resting length. You actually have to have a higher percentage of its resting length. So when the muscle is actually lengthened a good deal, it actually increases the tension provided in the muscle, okay? So a good example of this is if we look at these pictures, okay? And it turns out there's sort of an optimal length of the muscle to provide maximal force. In A, now we're going to assume she's starting here and then pushing up. So like she's starting a little bit squatted and then she's pushing up, okay? Now, when you're doing that, the quadricep is what's doing the concentric contraction. So the quadricep here is really not lengthened much at all, okay? Turns out that it's not lengthened enough to provide the maximal force. In C, her quadricep is very lengthened, but it's lengthened too much, and you actually won't get as much force from this length. Turns out that when you do a squat, this length of the quadricep is actually ideal, and it can actually increase the amount of force because it's lengthened a little bit more, okay? Lengthened greater than 100% of its resting length, okay? And this right here is showing the relationship between the force and the velocity of contraction, between eccentric and concentric contractions. Let's focus on concentric contractions first. There, it actually turns out that the force provided and the velocity of the contraction are actually inversely related. So there, if you expect to be able to contract the muscle very quickly, then the force that you have to be using is very low. Whereas if the force is really high that you're having to use, then the velocity is going to be much slower. Okay, so this is actually really intuitive. If you're doing a bicep curl, if you're curling some weight up with a barbell, if you've got a really light weight, you can get it up really fast. But if you've got a really heavy weight like you're maxing out, the shortening velocity of the bicep is actually going to be very slow. Okay? Eccentric contractions have a direct relationship between force provided and the velocity of the contraction. So actually, if you're doing an eccentric contraction and it's heavier, the object you're lifting is heavier, it turns out that the muscle will actually lengthen more quickly. And that makes intuitive sense. If you've got a bicep, doing bicep curls with a barbell, and you're extending your elbow, so you're lengthening the bicep. If it's a heavier weight, it's going to lengthen much more quickly. Okay? If you're lifting a very light weight and you perform an eccentric contraction of the bicep, it's going to lengthen a lot more slowly. Okay? All right, this was the lecture on biomechanics of skeletal muscle. Whenever you come in next time at the beginning of week 3, if you're on the Monday lab, or on Friday, you're also going to have a quiz over this chapter along with chapter 1. So make sure that you study for that. Thank you for joining us. Good luck.